Hello everyone, welcome back to the Logistic Regression series. So today we will be looking at gradient descent and ascent. I want to introduce to you to both the concepts just so that there's no confusion. Let's get started. Also, if you haven't subscribed, please do so that you know whenever I post a new video after hitting that bell icon, and then please leave me feedback because I do want feedback, positive or negative, in the comments so that I can make better videos for you. Okay, gradient descent versus gradient ascent. So before we jump into this, let's revise our log likelihood and cross entropy. Log likelihood and cross entropy. Okay, so log likelihood and cross entropy are closely related but serve sort of different roles, and let's try to understand why. So what are we trying to do? Imagine we have our fruit classifier with apple and oranges, right? And this predicts whether a fruit is an apple as a 1 or if it's an orange as a 0. Based on the features, maybe like weights and color. Okay, it does this classification. So what is the goal? The goal really is to train the model to predict the correct labels 1 or 0. And how? We need a way to evaluate how good the predictions are and then improve them, right? That's our how. So there are two common ways to do this. One is to maximize the log likelihood, and the other one is to minimize the cross entropy. And maximizing log likelihood, if we maximize log likelihood, what we're looking at is just basically telling it, hey, good prediction should have high probability. And then when we're trying to minimize cross entropy loss, what we're doing is telling it, hey, like bad predictions should be penalized. So we're essentially doing the same thing, but we're just doing it in a different way, right? Okay, so what does our log likelihood look like? Log likelihood. So the likelihood function tells us how probable the observed labels are given the model's predictions, and we've done like a deeper dive on this on the last video of the Logistic Regression series. So if you've missed that, please go check out the playlist and make sure that you look at why, how, about arriving on this. So this is what log likelihood looks like. What is likelihood looks like? We'll go to log likelihood. This is what our likelihood looks like. So if yi is 1, then we use y hat I, the probability of apple, and then if yi is 0, then we know that we use 1 minus y at high, which is the probability of getting an orange, right? So to avoid multiplying small numbers, because here we're multiplying all the numbers, and the sum of the probabilities could be as small as 0.002 or 0.003 or 0.00001, whatever it is. Sometimes when you're multiplying small numbers, it can lead to numerical underflow, right? And we don't want that. We want precision. We do not want any numerical underflow in our algorithms. So in order to avoid that, we do log likelihood. So we just take log of this function, and then with the properties of log, what we get is log LWB is then your I equals to 1 and yi log y hat I plus 1 minus yi log 1 minus y hat I. Okay, so this is what your log likelihood looks like. And coming back to intuition for this, if the predictions are good, then y hat is close to the level, that means the log likelihood is high. And then if the predictions are bad, that means y hat is far from the correct label, so the log likelihood is low. So here what we want to do is maximize log likelihood to make our model as confident and as correct as possible. Okay, so goal is to maximize log likelihood. Okay, that makes sense. Okay, now let's go and look at our cross entropy. So on the other hand, cross entropy, instead of maximizing log likelihood, we flip the problem and we define a loss function to minimize. So the cross entropy is simply sort of the negative of log likelihood. So our cross entropy in formula looks like this: I equals to 1 and y hat log of y hat plus 1 minus yi log of 1 minus y hat I. Okay, so if the predictions are good, and then your y hat, for example, is 0.99 for an apple, then the cross entropy is small. And if the predictions are bad, like y hat is say 0.01 for an apple, then the cross entropy is large, right? So cross entropy sort of acts as a penalty for wrong predictions, and then lower cross entropy means better model performance, right? So we're trying to minimize, the goal is to minimize here. So low cross entropy means better model predictions. So see how they're trying to do the same things, but they just have different perspective, different opinion of reaching there. So summarizing, what does log likelihood do? It measures how the probable, the observed labels are. And we have the formula. The goal is to maximize log likelihood. Sorry, that was my phone. And then optimization method is through what's called gradient ascent. So we're going to connect this back to gradient ascent. And then the perspective really is just how well does my model explain the data. On the other hand, for cross-entropy loss, it measures how bad the model's predictions are. And this is the formula. The goal is to really just minimize cross-entropy. So optimization method is through gradient descent, and we're coming back to this. And perspective is just how much error is in my model's prediction. So let me actually write this down, okay? So log likelihood, how does it think? Log likelihood thinks with how well does my model explain the data? Okay, so we are maximizing log likelihood. And on the other hand, sorry, I had to take a quick break, but anyways, so our cross-entropy loss, the perspective is understanding how much error is in my model's predictions. So this is done through gradient descent, which is minimizing cross-entropy. Okay, now let's talk about these two concepts and then tie everything together, because by this point you should be able to see where we're coming from in gradient descent and ascent, but let's just talk about it from their perspective, and then that should be clear. So how does your model learn? Your model learns by randomly guessing W and B, because at the very beginning it doesn't know anything. It starts with some random W and B and makes very terrible predictions. But we need a way to adjust the weights so that the model gets better at predicting our apples and oranges, right? So if it's correctly predicting apples, then that's great. But if it wrongly predicts apple, then we need to correct it, and the model should adjust so that the wrong predictions get closer to the right ones. And we can do this either through gradient descent or gradient ascent. It's either or. And I'll talk a little bit about why one is favored over the others, but I do want you to understand that when you look at other implementations, sometimes gradient ascent is going to pop up and sometimes gradient descent is going to pop up. Just know you can choose either. That's just because of certain reasons. One is preferred over the other in the industry, but mathematically you're reaching the same point. Okay, so gradient descent measures how bad our predictions are using our cross-entropy loss function. So what does this mean? In gradient descent, if we make a good prediction, then the loss is very small, and if we make a bad prediction, the loss is very large. So to make the model better, we need to minimize this loss. Okay, and in your gradient descent, basically all you're really trying to do is reach your minimum point by descending. Okay, so how do you start? You start with some random W, and then in the next iteration what you do is adjust your W with, this is your learning rate. Learning rate learning rate is how big of a step you're taking, right, towards reaching the minimum. So what you do is this minus learning rate, and then you look at so this tells us the direction of the steepest increase in loss, right? So you keep on taking the derivative, and then you you multiply it with the learning rate, and then you subtract this whole term from your last W in your quest to reach the minimum point. Okay, and again, like, we're subtracting because we're going downhill towards the lower loss. And for this, just think of it like you're skiing down a mountain sort of towards your lowest valley, and then gradient descent steers you in the right direction and keeps you moving downhill until you really reach the lowest loss. And then in gradient ascent, on the other hand, it's the opposite. In gradient ascent, instead of minimizing loss, we are maximizing how well the model explains the data. So what does that mean? We take our likelihood function, our log likelihood function, and then now we want to increase this function to improve our model. So we use gradient ascent, which moves uphill this time instead of moving downhill. So you take some random W, and then say you have your learning rate that decides how big or small of a step you're taking, and all you're doing is adding the log L by adding the derivative with the derivative times your learning rate, adding it to the previous W. So it's just like climbing a mountain, trying to reach the highest peak where your model makes the best prediction. So gradient descent helps you keep going uphill towards the higher likelihood, okay? Now, talking about why use one over the other. Both approach lead to the same optimal solution. It's either or type of scenario. In the industry, it's just minimization has become sort of the standard in ML, and it's going to come up in other algorithms. So you see gradient descent more frequently than gradient ascent because of that reason. And it's also used in other ML libraries. If you look at TensorFlow and PyTorch, I believe they also use cross-entropy loss. So it's just been like a industry standard. But at the end of the day, both approaches, they just lead to the same solution. So it's just different perspectives. Gradient descent is just more common, but feel free to use any that your heart desires when it comes to practicing. That is pretty much it about gradient descent and ascent. I hope the intuition is clear. But let me know if you'd like me to do a deep dive on any part of this. We're getting closer and closer to implementing it from scratch now. I hope this is clearer.